Engineering Studies, the Definitive Guide by Paul Copeland. This is in Volume 1, and we're going through the second half of the first chapter. We're picking up from Simple Machines, and this is going to be more of a summary rather than an in-depth lesson. So the first thing is, when I talk about Simple Machines, I usually talk about I used some videos that are pretty old from Canada, and they're called Eureka. So I'm not going to show those videos now. Instead, I'm just going to go through my questions that relate to them. But most students I have taught have said that they found them pretty easy to understand, and they were happy to go through it. So my questions that go with that video are: a simple machine does not change the energy required to do work. However, it reduces the something, increasing the something. So the idea is that if we had something that was very heavy, let's imagine it was a 200 kilo vat of oil, then most people wouldn't be able to lift 200 kilos. But instead, if they separated it into lots of 10 kilos, they'd probably be able to do that. If they poured the liquid into 10 drums, they would be able to carry 10 kilograms, or engineers would probably be better off using the term 100 newtons, and they could carry that 100 newtons, and they could just carry it 20 times. So in carrying it 20 times, they're going to walk back and forth between point A and B 20 times, but they're requiring a lot less strength or a lot less force in order to carry that load. So when we use simple machines, we're not talking about things like compressors or motors or other things that use electricity or burn fuel, things like engines, to do work. What we're talking about instead is just when we use regular everyday objects to help us do the same amount of work, right? We're still going to need the same amount of calories, the same amount of energy to do the work. The difference is that we're going to increase the distance that we need to do the work, or increase the time that we're going to use to do the work. So work is measured as force times distance. So if we need to carry a 200 kilogram barrel, or if we call that a 2000 kilonewton barrel, and we need to carry it 10 meters, what we're interested in is 2000 newtons times 10 is going to be 20,000 newtons, or 20 kilonewtons. That's the amount of work we need to do. And so when we measure it, we don't measure it in Newton meters. Instead, we measure it in a unit called a joule. It's the same as the others, where we use the capital J for when we use a symbol, or a lowercase word joule. And joules are also the same unit that we measure food in. When we eat food in kilojoules, or we can use the older term calories. Calories is just a measurement of measuring energy. But the difference is that the energy that it measures is using water as the constant. That's why it's 4.2 times bigger. Whereas kilojoules is a more precise. That's the SI unit. So we use kilojoules rather than calories. I have a meme, a Drake meme somewhere floating around, but I'm not going to find that now. Maybe I'll splice that in later, but probably never will. But the idea is that energy and work, the same way that stress and strength are measured in the same unit, stress and strength, they're both measured in what unit? Pascals, right? Work and energy, they're measured in the same unit. They're both measured in, when we use SI units, we use kilojoules. So we use joules. Typically, when we talk about food, we measure things in kilojoules. The energy generators, power plants, they might measure things in megajoules. So energy actually comes from the Greek word. It means work in. Ergon meaning work. Energy is the ability to do work. Okay. So to fill in this, if you can fill in your sheets, when we use a simple machine, it reduces the force needed by increasing the work. A ramp is an example of something plane. Starts with an I. Inclined plane. So if we look here, we have two simple machines specified here. We have a lever and we have an inclined plane. So they're the two simple machines that we typically talk about. Some people say that all simple machines can be classified as either levers or inclined planes. That's kind of true. but it's not entirely true, because pulleys are a little bit more confusing. So we're going to start with inclined planes, and the idea is that if we have to lift this wheelbarrow, in this case they're saying that the mass of the wheelbarrow is 10 kilograms, that if we were to lift it, it's the same amount of work if we lift it 10 times, well, I'd like if it had gravity, yeah, but then it needs to multiply by the distance. The point is here that it's easier to push the wheelbarrow up a ramp, but it's going to take longer than if we just lift it straight up. Does that make sense? Yep, okay, great. So the next one we're going to talk about is to balance a lever such as a seesaw, you can move the heavier weight closer to the, well, okay, so before we finish that one, so when we have lever, so the lever, most people are familiar with levers when we talk about things like seesaws. That's the quintessential lever that people talk about. I don't know if seesaws, you see them very often in parks, but most people seem to know what a seesaw is. The idea is if you have a plank of wood just on any sort of pivot in the middle or a fulcrum in the middle, that what you can do is you can balance two objects. So even the old, when we think of the ancient scales, they're another form of lever. But there's lots of other levers we use in our day-to-day life. Things like crowbars and fishing rods. And so the idea is the same, that what we can do is we can magnify our effort, or we can magnify our force by increasing the distance or the time that we use to do it. So in the case specifically of seesaws, a friend of mine, he used to have a larger fellow, used to wear a t-shirt that said fat kids always win at seesaw, but that's not necessarily true. If we move the heavier weight closer to the balance, closer to the fulcrum or pivot, you can write there, so that the distance, the force is multiplied by the distance to the fulcrum. So if the heavy kid is only 1 meter away and the lighter kid is 2 meters away, well, a lighter kid will be able to balance a kid who's twice as heavy if they're twice as far away. Yeah, because those two things, because it's force times distance, those two things will balance. And we'll learn more about that when we learn about moment forces later. Okay, so the next concept we need to learn about is mechanical advantage. Before I jump to that, I will, using Copeland's notes, I'm going to go instead, I'm just going to talk about the screw is an example of what? It's 2 words. What simple machine has 2 words? Starts with an I. So a ramp or something like that. An inclined plane. So the idea is that a screw is really just a ramp that's been spun around an axis. So that if you're going up a spiral staircase, it's the same amount of work as going up a regular staircase. The difference is that a spiral staircase goes around, and we call that a screw. And that a screw can be used to do the same thing. A screw can be used to increase the amount of force you can apply by stretching out over a longer distance. Okay. The other famous one, so these are all covered in the Eureka videos, but the other examples are wheels and axles. So there's a video that goes, a different video that goes into some good detail about this, and we're going to come back to that one. This video is spinning levers. I think does a really good, it's again very old, and generally if a teacher is using something that's 40 years old, or in this case I think it's closer to like 80 years old, is that right? Yeah, probably. That it's probably a good sign that it's a good video. So it seems a bit silly, but it shows some examples of levers, but then it shows how we can the evolution of where we go from a simple lever So we can see here how, in this case, the 25 pounds was able to balance, the 25 pounds was able to be balanced by 5 pounds by making the 5 pounds be 5 times further away. The moment forces, which we'll learn about later, are balanced. So the video goes into a lot of detail. It talks about how gear transmission works. Things a really interesting video. But I think that demonstration makes a really good example of how what we can do is we can take levers, and if we continue levers, we can get wheels, and we can also get things like gears and belt systems. So that we also have, in this video here, we show pulleys, and we also show belt drives. So things like mines, they use a lot of belt drives to power their conveyor belts and things like that. You know, your car will have fan belts to power things rather than using chains. Okay, so let's go back here. So the screw is an example of an inclined plane. The wheel and gears are examples of, starts with an L? Levers, yeah, levers or levers. There's only two, we're only talking about only two inclined planes. Okay, so they talk about, if we watch the Eureka video, we'll have mechanical something can be calculated by dividing the something force by the something force. And what that does is that when we want to talk about how efficient a machine is, how useful the machine is we can compare the input force to the output force. So the idea is that if I have a lever, let's say a crowbar, allows me to lift an object that weighs, let's say 200 newtons, right, a 20 kilo block. I can't lift a 20 kilo block comfortably, so instead I might use a crowbar, and the crowbar might allow me to only use, let's say, 5 newtons of force. What would be the mechanical advantage? 20 divided by 4 is 5. And in the example that we saw earlier, where we had the 25 pound weight being balanced by, in this example here, where we can see a 25 pound weight being balanced by, well, here we have 10 balanced by 2, and that's because the 5 pounds is twice as far away. I appreciate I'm using imperial units, but I think we could substitute pounds just as easily for kilograms. It would be the same example, or any unit. What we can see here is because this is twice as long, this lever is twice as long, so the mechanical advantage in this case is 2. Now, there is some variation between mechanical advantage for what we see and what we can predict. So in this case, the distances and the weights kind of balance, but that isn't always the case because not every machine is perfectly efficient, right? And we're going to learn about efficiency later. In this case here, we have 25 pounds and 5 pounds. What's the mechanical advantage in this case? 5, because what we're getting out divided by what we're putting in is 5. So the output divided by the input is the mechanical advantage. So that's what we're going to write. The mechanical advantage can be calculated by taking the output force divided by the input force. So here we're getting 5 to 1, and we're getting an output of 25 pounds and an input of 5 pounds. Now, in the next case, they talk about how the difference between these two cranks, right, these levers here, is 4 to 1. So we can predict that we're going to get a mechanical advantage of 4, but by looking at the distance, we can predict the output. But we don't necessarily know. It might not be a full 4. It might be 3.8. And that's because of things like friction and resistance, air resistance. They can make our machines heat, loss of energy due to heat. They can, which I guess is what friction is. They can reduce the efficiency of our machine. So later we'll talk about things like mechanical advantage, and we'll compare it to velocity ratios. Velocity ratios are what we predict, and mechanical advantage is what we observe. Does that make sense? Yeah, mechanical advantage is calculated by comparing forces, where velocity ratio is done just by comparing distances. So in the case of, if we go back to Copeland's distance here, we can see that we could use the distance of this ramp to predict. So we could say that if we knew this distance compared to the height, we'd be able to calculate not a mechanical advantage, but a velocity ratio, or a perfect, in some cases they write IMA, so which is the perfect mechanical advantage. And because it's never realized, it's virtual, we call it the velocity ratio. And what we find is that in the Eureka video, they talk about how levers are more efficient than ramps. For the same dimension, for the same velocity ratio, we'll get better mechanical advantage because levers are less affected by friction. Okay, lastly, the last video they talk about on the Eureka video is a pulley must be something to offer, I've got offer twice, mechanical advantage. What does a pulley need to do to be able to offer mechanical advantage? Well, with pulleys, we can calculate the mechanical advantage. Well, to calculate a mechanical advantage, what do we need to know? We need to know the forces, that's right. So to calculate a mechanical advantage, we really need to do an experiment. We need to look at a pulley and see what we get. But if we want to calculate instead the velocity ratio, right, we can look at a pulley and we can make a prediction. We can say what the velocity ratio should be, and then we can compare that to the mechanical advantage that we observe. So in this case here, this one here has a mechanical advantage, or a velocity ratio more correctly, of 5. And how do I know that? Well, if you watch the Eureka video, which I'll just quickly highlight so that you know what I'm talking about. So in this series of videos, so I only just have the link to the first one, and I have the link to a list that shows all of them, a playlist that shows all of them. The last one talks about how, I'll quickly open that and talk about it. So they show Jack and Jill, and they're trying to get some water out of a well. And what they found is that if you just tie a rope to the well, we want to go to episode... playlist, and we want to go to pulleys. They're all okay. The other ones on chemistry, I do recommend if you're interested. And they will cover the content we're going to talk about next. So if you have a rope, well, you're going to have to do the same amount of efforts, right? If you use a rope, if you want to lift up a 20 kilo bucket, it's going to be 200 newtons. You're going to need 20 newtons to get that bucket out of the water. But in this case here, if you just use a simple pulley, all that will do is change the direction of the force. It won't give you any mechanical advantage. So in this example here, this will not give you any mechanical advantage. Neither of these will give you any mechanical advantage. All they'll do is just change the direction. To get mechanical advantage, what you need is a moving pulley. You need to add a second, so this is a single fixed pulley, but if we have a single movable pulley, we're now going to get mechanical advantage. And then we can increase the mechanical advantage further by having more pulleys. So if we have a second pulley, right, we now will get a mechanical advantage. I would predict that should have a mechanical advantage of 3. And how I can tell that, the rule that I use is I look at the moving pulleys. Remember, without moving pulleys, you don't get any mechanical advantage. What we have is 3 ropes touching the moving pulleys. So earlier I said this one here has a mechanical advantage of 5. Let's have a look. Well, we can see that these pulleys on the top, they can't move. They're stuck to the roof. It's only the pulleys on the bottom that are going to move up and down. So if we look at how many ropes are attached to those pulleys, we have 1, 2, 3, 4, 5. So we should get well, in a perfect world with perfect efficiency, we'll have a mechanical advantage of 5. But in fact, we would be better off saying that it has a velocity ratio of 5. Now, like I said, I recommend those Eureka videos, but there's not really a lot of value in me showing them now. Wikipedia has a good resource where they talk about how you can determine mechanical advantage, where we can actually see that the amount of rope that you need to pull, if you have a single fixed pulley, single movable pulley, we actually pull the rope twice as far as the object moves. So the object's going to move 10 centimeters in this example, whereas the person who's pulling the hook, they're going to be pulling 20 centimeters. When we have 3 ropes touching the pulley, we have 3 times the distance. So that's how we measure our velocity ratio. Here with 4, see how there's 4 ropes touching moving pulleys? 1, 2, 3, 4. With 4 ropes touching moving pulleys, we get a mechanical advantage. Well, no, we get a velocity ratio of 4. Now, Khan Academy has a video where they go into a lot of detail if you really want to learn more about